Hello, I'm Shujaat. I'm a PhD student at BISPL KAIST. Here I will present to you my recent work on deep learning based deconvolution ultrasound imaging. Let's get started. Ultrasound imaging is based on acoustic signal, and due to its non-invasive, radiation-free and real-time acquisition features, it is considered as the first choice for a variety of clinical applications such as feeders or cardiac imaging. It is a robust imaging modality. However, it suffers from low frame rate and poor imaging quality. Since the axial resolution of the ultrasound is confined by the quality of the transducer as well as the number of transducer, which has limited bandwidth, therefore high quality ultrasound imaging requires large number of measurements that result in increased cost, size and power requirements. On the other hand, there is an increasing demand for the low power portable and 3D ultrasound imaging systems. To address the aforementioned issue, compressive deconvolution ultrasound provides a reasonable solution by solving the blur function from the limited acquisition scenario. However, it has its own downsides such as high computational costs and the problem of accurate estimation of point spread function. According to the deconvolution model as shown here, the RF image can be represented as a convolution between point spread function and tissue reflectivity function. The quality of the recovered image is linked to the beamforming technique. Now the aim of the ultrasound reconstruction is then to find the beamforming or beamformer weights and deconvolution filter matrices, which are B and B tilde, so that the process image has high resolution and good signal to noise ratio. In practice, the estimation of this tau, which is composed of B and B tilde, is technically challenging, and the filter matrices should be spatially varying and also depend on input, so that we can find a best trade-off between signal to noise ratio and resolution. Therefore, the exact calculation required high computational power or high memory, and that's why we usually actually choose to use approximate forms, which result in limited accuracy. A quick remedy to reduce the runtime computational complexity would be using a pre-calculated tau, which we have already stored or which we can already store for multiple inputs. But then, unfortunately, as I stated before, the mapping should depend on the input, so it required huge memory to store tau for all possible combinations. In this regard, a convolutional neural network using ReLU nonlinearity provides an ingenious way of addressing the issue. Specifically, in a recent work, we show that the universal deep beamformer model can perform deconvolution ultrasound to generate high quality images from low quality channel data, which is subsample RF data. This will alleviate the need of PSF estimation. However, for many portable systems, access to the channel data and high quality label images are not available. Therefore, we provide a method which is based on image to image deconvolution. And the proposed deep deconvolution model can be trained in an unsupervised manner without any patch reference data. So we can get high quality image from a low quality image, and we can train a model without any RF data or paired images. To design an image to image deconvolution method using unpaired data, we acquired RF images from tissue mimicking phantom and in vivo scans of 10 volunteers using focused beam mode imaging. The in vivo images were acquired from calf, forearm, thyroid, and carotid regions of different volunteers, and a single model is trained for variable subsampling rates to generate fully sampled deconvolution images using low quality DAS images. The configuration of the ultrasound system and the sampling scheme is shown here. We use Alpinian system and the probe configuration is shown here. We use variable subsampling rate just to show that any pattern or any combination will work, but if you have particular requirement, you can choose a particular sampling scheme. For example, uniform sampling where you use only center elements. But we are just showing it that there is no the method has no limitation. You can use any sort of sampling pattern. For target images, we we are not using direct simple deconvolution because conventional iterative methods used for the deconvolution are very slow and also require parameter tuning for different scenarios. Therefore, it is not suitable to use iterative method to generate large amount of data. Since image to image method may require large number of images, that's why we choose a different approach. For target domain images, first the DeepDeconv model was trained on a small dataset to mimic the deep deconvolution method, and later the fully trained model was used to generate high quality deep deconvolution images using fully sample RF data. The output of the iterative and the deep DF deconvolution is shown here. As you can see, the result of the DBF and iterative deconvolution are quite similar. So we can use the DBF deconvolution images as our target images, which has a similar quality as DES deconvolution. To train an unsupervised deconvolution model, we propose a network architecture shown here. The model is composed of generator and discriminator networks arranged in a cyclic fashion shown here. The cycle consistency and LS gain loss function are used, resulting in a stable training using unpaired images. Interestingly, our method has no need for the PSF estimation. It also does not require any pair high quality data, and it provides a universal model for variable subsampling rates, which can be used for generating high quality images from different sampling configuration. A single model is enough for all variable sampling cases. The trained model is evaluated for standard quality measures such as PSNR, SSIM, and CR, contrast ratio. Figure A shows B mode images from fully sampled data of in vivo and phantom tissue mimicking phantom. Overall, a single universal model, which is one-time trained for all sampling rate, produce significant performance gain in terms of contrast and resolution for all sampling rates. The models compare with the DBF, DAS, and the same model which is trained in supervised fashion. So from the images, you can see there is this slight like just minor difference in the supervised and unsupervised and DBF images. However, when you compare it with the DAS images, the images look quite sharp and has better contrast. A similar result can be seen in the figure B, where we use different sampling rate. It is noteworthy to point out that the same model is used for all cases, all images, and no training is performed for each scenario, which means a model is trained once for all cases and the same model is used for all images, which means no further training is required. A single model can be used for variable sampling rate. Here you can see the image quality is much better than the subsample case of the DAS. The same can be seen in the performance statistics, is shown here, that the method maintains its performance while the DAS, the quality metric in the DAS actually drop very fast, and it's actually drastically reduced the quality. So we can conclude this study as follows. The proposed model enhances the image quality by improving the contrast and the resolution of the low quality DAS images. We show that the universal model can help improve visualization quality of the DAS images acquired at low sampling rate. An unsupervised image domain learning strategy can alleviate the need of a paired dataset as well as the PSF estimation Hence, it is easy to deploy. Therefore, this method can be an important platform for efficient ultrasound imaging. Thank you for your attention.